Copyright in these lectures is either owned by the ANU or a third party who has licensed the ANU to use it. Students may use the recording for personal study only. No lecture may be communicated online, copied or shared without the prior permission of the ANU.
So the only command that's it basically, when I give you some code for this sort of stuff, the only command I'll give you is something like a library command like this. And the library commander usually assumes that you've already done at some stage and stored the necessary package in the background. So the packages we're going to want are LME4, that's the fourth version of the LME one. So then you can basically, once you've installed the package, got the correct spelling of the name there, you can then basically load the library. Because there's certain commands that you don't have available until you've loaded that package. So I think the tape's actually started now. So I'm just warning people for tomorrow, when we're going to start on random effects models, that you'll need some extra packages. The packages concerned LME4 Applied Regression Modeling, which is the Geller textbook, and the other one I occasionally use is NLME. Okay, so NLME seems to be part of standard R and gets loaded quite quickly. So hopefully you've already got that one available. If you haven't got the package available, then you'll get a message saying something like this, saying there is no package called ARM. What you have to do then, and I might set this going so that it works for tomorrow, is you have to go install packages with the name of that package. You can do all this from the menus, by the way, as well. There's menu options for doing these. Okay. So hopefully everything will work seamlessly tomorrow morning. Because otherwise, it can be a fair wait to get these things to work. Okay, so we'll come back to that. Hopefully it'll run in the background while we're doing all that. So where are we? Essentially, we've gone through workshop 2, which was about one-way analysis of variance model. I need to make a few concluding remarks about the one-way ANOVA model because we're going to start extending that to all sorts of other different sorts of models. And that means I've got to introduce a new notation, which means I've got to do it fairly slowly because otherwise people will get lost quite quickly. So we'll come back to this example in a second. We went through a couple of things about the analysis of this one, so I need to sort of cap off the analysis of the core yields data. One thing I don't do most of the time is I don't produce lecture notes. I've got the lecture notes, but as far as I'm concerned, I helped write those. They're my version of this stuff. If you want a different version, the faraway text gives a version with a lot more detail most of the time. If you want to get a summary version, well, don't come to me for the Twitter version. If it has to be expressed to 140 characters, I probably can't do it. Okay? I'm not a creature of Twitter at all. Donald Trump and I disagree on that as well. Okay? So, if you do want the Twitter version, i.e. a short, succinct summary on a slide, that's the way you're doing things. Well, Bronwyn Long taught this course about 4 years ago in my place when I was having another break. And she produced lecture slides because that's her way of doing things. And so what I have done is I've made those slides available to you. Often, though, Bronwyn, of course, chose a different example because she was actually trying to teach from the Andrew Geller text, which is on your list of references, which I think is a little bit too detailed for given the mathematical background most of you have. It's probably a good textbook for the ones that are just doing this as a statistics course, doing it for statistics' sake. That's the applied regression modelling text. It's the hierarchical models text. So look, I'll make sure you get the reference right for those that need it. It's in here. So if you really are trying to get yourself a major in this sort of stuff, the Andrew Gelman and Hill, I can't remember Hill's first name, but Gelman's is the real force behind this. That's the name of the current edition. It's a good book, but it's a good book for people who've got the mathematics and they've got a little bit more. So I wouldn't be happy using it as a text. I'm not particularly happy with using the faraway text as a text either, because I think there's just a bit too much detail in there. Okay, so here's Bronwyn's slides. And so if you want a third version, remember my rule of 3. If I've stressed it at least 3 times, it's an important part of the course. It's probably not a bad idea to go through different versions of this sort of stuff until you've got most of the basic points down. Like I said, Bronwyn used a different example. I've also made that example available on Wattle. But, it's not much different from the core example anyway. It's just a simple one-way analysis of variance. It probably doesn't have the issue with outliers, or it seems to have a little bit of an issue out there with outliers. But then she gets back to the stuff I'm going to quickly do now for you, pre-see what's in the brick, describing the models that are actually fitting here. Okay, so she goes through the description of the model. Again, if you found the brick stuff confusing, you might find Bronwyn's stuff equally confusing, or it might help. Like I said, please have a go at both versions. But really, I'm going to try and talk you through them now. There's also the idea of basically doing comparisons between group means. We talked a bit about that the other day. And we also talked about the issue of multiple comparisons. Now, the solution you would have used in a regression modelling course, and I presume Anton introduced you to this if you did in first semester, is the idea of doing at least some sort of correction for the issue of multiple comparisons. So if you are going to make multiple comparisons, you're going to make multiple tests. The overall confidence for all those tests is not 95%. Even if you assume them independent, it's going to be something like the order of 95%, 0.95 times 0.95 for the second comparison times 0.95. You quite quickly get below 95% overall. Okay? So one solution you have that was probably explained to you in regression modelling was Bonferroni correcting. Instead of using 95% confidence intervals, you work out how many comparisons you're going to have, and you adjust. Okay, well, I'll quickly run you through how we do the adjustment. There's an example in the brick, but I'm actually not going to use that most of this semester. I'm going to because I thought it was an issue in the previous course, I'm going to skate over it as an issue in this course. However, as a practicing statistician, you need to be aware of when you are in the realm of multiple comparisons. When you've basically got to the stage where you've torturing the data enough, eventually it will confess to anything. If you do enough tests, eventually you'll come up one that's just basically wrong for the wrong, that seems to be significant but is not significant, shouldn't be significant. It's actually just turned up to have a positive p-value for the wrong reasons. Okay? So the Bonferroni method basically sort of says if you're going to make, so 1 minus alpha is the confidence level usually. Alpha is 5%, so we're talking about 95% confidence intervals. So if you're actually going to make a number of comparisons, you're going to have a number of different comparisons, G of them say, then what you should do is you should have the confidence, you should use the confidence level of 1 minus alpha on G. Okay, so divide your 0.05, let's say you're making 3 comparisons, divide it by 3, and you make one, so you make it at, that'll be the 1 and 2/3 level of significance. 1 minus that, you'd make everything at 98 and 2/3%. Okay, and then you've got 3 of them. Your simultaneous confidence is something of the order of that cubed, which ends up being about 0.95. Okay, that's how Bonferroni works quickly in a nutshell. There's a few probability calculations in there, and there's a few assumptions about the comparisons being independent. And I'll run you through an example again in a second. But really, the important stuff was that really what we want to do is we want to make comparisons about contrasts among the means, and there's a general formula here for doing that. This is not Bonferroni corrected because there's no G in there, and that's typically what I'm going to do as well. I'm going to adopt what's called the Fisherian approach, named after Fisher, because what Fisher did was he didn't view these things as a decision thing where you just say yes or no in a sort of, a trained parrot-like fashion. You set up everything and then basically make a decision on that. You actually weigh the evidence. Okay, so as far as physics is concerned, none of these things are particularly conclusive anyway, and he probably wouldn't use p-value as a yes-no decision-making tool anyway. What Fisher would do is he'd do at least one comparison to start off with, or one key test to start off with at the right level of confidence. And if there was something to find, then it would go fishing for for the effects that seem to be important in this instance. In other words, he'd have one test that sort of say, look, I expect to find something going on here, and then he would basically trawl through until he found one, even that involved making quite a few comparisons. That's in the post hoc fashion. If you're doing an experimental design, of course, you can plan all these. So in an experimental design situation, Bonferroni correcting is probably not a bad idea, because if you know a priori before you start that there's going to be a couple of key comparisons you need to make, or 2 or 3, and you know what they're going to be, i.e. they're part of the experimental design, then it's probably quite a sensible idea to also plan to do it in a Bonferroni corrected basis as well. Okay, so there are two sides to the coin here. There's 2 ways you can make this decision. Okay, so let's try and put there's a few numbers around these, because with the example Bronwyn was using, she was really stretching a point because she was going to go and sort of say, well, I could do 6 possible pairwise comparisons between 4 treatments. And really, we don't need to do that many in most situations. And even if we're planning the experiment, we probably don't need to plan for that many. Okay? She was really labouring a point. Okay, so I'll leave you the rest of the Bronwyn slides there. Like I say, there are typically 3 takes on this material, on most of the material in the course. There's the stuff I do in lectures in front of you, that are on the tapes, on my handwritten notes, in the brick, in the lecture note brick. If you like, that's my version. There's Faraway's take on it, and there's Bronwyn's take on it as well. I encourage you to read as much of those until you think you've got the major points in each of these bits of material. So, there's Bronwyn's slides, which I have briefly discussed now, and there's the example she actually used as an hour example with the data. So if you want to run through that, you can do that as an exercise and have a look at her early slides. So back to the corn data with me. So, first thing I have to do is attach the corn data. I'm in the right database. This is the one I used for, I started up from the workspace I was working in last time. And so all the history is still in there somewhere. But the one thing we don't do is don't have the corn data attached automatically. We have to reattach it. Okay, so we came down to a couple of models that seem quite good. right at the end here. Now notice I have added a little bit of stuff in this one, so if you took a copy over the weekend, you probably need to take another copy. So, the model we finally decided on was this one. That's this analysis of variance table. Sorry. And we were using this even though we thought there was a bit of a problem with the variance in one of the groups. We decided not to eliminate two of the observations, because in doing so would unbalance our design, make things a little more complicated. And the argument was that at least any inference we did now would be on the side of being conservative, because what we've got is something inflating the underlying error variance. Typically, before I delete outliers, I prefer to check what made them an outlier, and I can't do that in this situation because I don't even know where the data came from. The normality stuff, not really a problem, but again, it looks like 1 and 2 are a little bit away from everything else. Don't talk about that plot. And this one is basically, you know, sort of with the nicer labels, because it's an AOV object, or actually because it's an LM object in this case, but it's a sensible thing to do in this context. Okay, so have a look at the analysis of variance table here. What's that F statistic telling me? What are we really doing here? We're comparing the average yields for the different groups, aren't we? Okay? And so it's really telling me that there is some differences between those average yields. Some of these groups are not like the others, to quote Sesame Street. Okay? So there's something, in Fisher's terms, there is something going on here. That's my key test made. That's my key test made at the 95% level. 95% confidence, 5% significance level. Okay, so I could then trawl a bit further and find out what I think is going on, and that's an excuse to go to this. Here's the summary thing. Now notice I fitted this using treatment contrasts. So this was actually the mean for the control group. That was how much I had to move from that mean to get to the mean for the second fertilizer group, which was the K2O plus nitrogen. That was how much you had to move to get to the third group, which actually seems to be worse than putting no fertilizer on. Okay, if anything, it's actually inhibiting corn yield. And this one is the fourth group, the other, I can't remember, the nitrogen plus phosphate group. Again, we have to, it'd be nice if we could force our labels onto these. I'll show you what tricks for doing that later on. So, there is something going on according to that first test. What seems to be going on? Yes, fertilizer 2 has a significantly higher yield than the control group. So all of these three comparisons here are comparisons between that fertilizer group and the control group. Okay? So in fact, again, I've now made three comparisons. So again, I could do something like bond for any, I could calculate confidence intervals for each of the effects of the different fertilizer groups. And I could bond for any correct them for the fact we've got three of them. Okay? And in fact, that's what's done in the code a bit further down. So, to do that, I'm going to need a few things. first of all, I'm going to need the estimated mean squared error. So remember the key error variance parameter here is sigma squared, and I can get that from the analysis of variance table, the estimate of it. It's there. Okay, is it stored somewhere nicely for me? Well, if I look at the names in the summary, I find there's one called sigma. What's in that? A quick check. Square it. And whoa, it's 163.6, which is the error mean square. So I've got sigma stored away somewhere nice and handy. Okay, then I had to do the rest of that that pairwise means stuff, which I think is further back in. I don't like the way Bodmer writes them out, so I'll do it myself in a second. But basically, I'm just comparing two means. Really, I just need my standard error for that comparison is going to be sigma. It's going to be the square root of, well, the variance of the first group. But what am I assuming about the groups? I'm assuming all the groups have equal variance. So I'm assuming they all have sigma variance, sigma squared variance. So the variance in all the groups is sigma squared. It's 163.6 is my best estimate of it. Remember, the standard error also involves dividing by the sample size. Okay, so I've got sigma 1 squared over n1, if I'm comparing group 1 with some of my other groups, plus sigma, well, if I'm comparing 2 with 1, I can play sigma 2 squared over n2. Okay, but n1 and n2 are both the same thing, so it's a balanced design. They're both 6. Okay, so really my standard error, in fact my standard error is shown for me here, 7.385. It's the same for any comparison of any two groups. Okay? Because I want to remember how we did it in last week? We formed a contrast vector called H, where H was what do I want of each of the elements of each of the means. So if I want the second mean minus the first mean, then I've got 1 squared times sigma 1 squared on n1 plus, well, the second, I probably shouldn't do this as a hand waving exercise. I probably should do it with a bit of writing it down. Did I write it down well enough last week? Let's have a look. See people's eyes glazing over, so we'll go back to doing it. Okay, so in that sort of sense, if I was comparing the second one with the fourth one, I basically have a contrast vector of 0, 1, 0, minus 1. So it's 0 squared, so I can take the s squared out the front, because basically it's the same for all of them. It's the same sigma on top. So I've got 0 squared plus 1 squared plus 0 squared plus minus 1 squared on n1, 2, 3, 4. But these are always the same. n2 equals n4 equals 6. Okay, so I'm comparing any two of them. I'm going to have the same standard error. It's going to be whatever my sigma squared is times 1 on 6 plus 1 on 6. Take the square root of all that, because that's a variance. I get my standard error. So there's the standard error, and surprise, surprise, it's the standard error that's shown here, because each of those lines in the summary table is actually doing that comparison. It's comparing fertilizer 2 with fertilizer 1, which is the control group. So 7.385 is the appropriate standard error. Here's my estimated deviations away from my control group. There's 3 of them, so I've actually got 3 comparisons there. I've got 3 lines in that summary table. So I should bond for any correct those. Well, to get the right t quantile, I have to go the quantile for 1 minus 0.05. That's the 0.95 quantile. But I have to divide that by 2, because actually what I want is the 0.975 quantile. Because the bit, I want the 95% between 0.025 to 0.975, the 95% in the middle. And if I want to bond for any correct, because I'm doing 3 comparisons, I multiply that by 3. So there's my G creeping in. And the degrees of freedom associated with this are the degrees of freedom for the residual standard error, or the degrees of freedom shown, I've gone too far, here, the residual degrees of freedom in the analysis of variance table. Because the key unknown here is sigma squared. I'm estimating using a thing that's based on 20 degrees of freedom. Does all that make sense? So if I run those and run the uppers, let's C-bind everything together so I can actually look at a comparison. So here are 95% confident, well, they're not 95% confidence intervals, they're actually 98.33% confidence intervals. And if you cube that, you get roughly 95% for the 3 of them. Okay? So, if you like, they're Bonferroni corrected or simultaneous confidence intervals for the 3 comparisons at once. And notice that the lower and the upper basically bracket 0 for these 2, indicating they don't differ from the control group. But this one is entirely, even Bonferroni corrected, it's entirely above the control group. So the conclusion there is that fertilizer treatment gives a better yield, even Bonferroni corrected, than the control group. Okay. So how does the Fisher version work? Well, I think I need to do a little bit more on the document camera, and then we'll talk about how Fisher would get around this. So the first thing I want to do is talk you through the actual model that we're fitting here. So, it's the one-way ANOVA model. Bit of jargon. It's called one-way because there's only one factor. The differences in fertilizer treatments is our one categorical factor variable we've got here. So, we were using treatment coding. I defined the dummy variables for that earlier on. Really, in regression terms, what I'm doing is this. So, I goes from 1 up to n equals 24, and the errors are assumed IID, normal, 0, sigma squared. That's just supposed to be a colon there, so I might just get rid of it. So that's the model we fitted, typically the model we fitted in regression modelling. And the way we've coded up the categorical variable is we've coded up 3 indicator variables to represent the different levels, the levels other than the control group, and they're all 0, 1 variables. But the thing we can notice about that is that the interpretation of these is this was mu naught, which was the mean of the control group, this one turned out to be mu 1 minus mu naught. I'm actually going to use naught for control and 1 for the 2, 3 for the 3 fertilizers, because it makes a little more sense when you write it out that way. Let's call that tau 1. Similarly, B2, the interpretation of B2 was mu 2 minus mu naught. Call that deviation 2. And B3 was mu 3 minus mu naught, and we'll call that deviation 3. Okay. So really, there's only one variable here, and we've got 3 terms. Well, it's right. It took us 3 degrees of freedom to fit it. The analysis of variance table tells us we've only got one variable, but it's got 3 degrees of freedom associated with it. And that model actually corresponds to what we see in the summary table, doesn't it? So the old-fashioned regression model way of doing things actually corresponds to that. Here's the shorthand notation we're going to use from now on, because it really is shorthand. The EIJs are still IID normal 0 sigma squared, but really what we've done is we've condensed those 3 terms there into a single term there. Okay, and that's actually a good model for reflecting what's in the analysis of variance table. There is only one variable involved here, and there's only one term for it in that shorthand version. Okay. But we're not finished, of course. We now have to sort of say, how do we set all this up? Otherwise our description of the model is incomplete. Well, I mean, where Yij equals observed yield, the observed yields, and J equals the levels of our FERT, which is basically, I'm going to call them 0, 1, 2, 3, because really okay, so really there are four different categories. It's easy, it doesn't matter whether I number them 1, 2, 3, 4, number them 0, 1, 2, 3. Just 0, 1, 2, 3 corresponds quite neatly with, really that's associated with that. The beta naught is going to be the mean for the control group under this one. And the I equals 1, 2, up to nj equals 6 for all j. So I've got six replications for each of my 4 groups. And in fact, in experimental design terms, what I've got is I've got 4 fertilizer treatments. Which are those 4 things there, times 6 replications per treatment for a total n equals 4 times 6 equals 24. And I do have 24 observations in my data set. There's one thing missing in all this. What's missing? As you saw, I could have coded this model quite a few different ways. The 2 main ones were treatment coding, which is the version I actually used because I thought it was more interpretable in this situation, because it allows me to compare each of the fertilizer treatments with the control group, the absence of fertilizer. Or I could have used sum coding. How do I specify the difference in these model specifications? Well, essentially what it means is that one term I have got here, the main effects term, the one-way term I've got for just that fertilizer treatment, is constrained. How is it constrained? Well, it's a treatment constraint. So what does that constraint involve? You know, remember the sum constraint was sort of saying that all the parameters for the different 4 groups had to add up to 0. The treatment constraint was setting one of the levels to 0. So, to specify the parameter coding used, we also need to specify the constraint okay. And in fact, that's a complete description of what we did. You're probably have to do a bit of work on this before you can work out how to fully specify some of these models. Let's face it, you don't need this description for the client. Client comes into your office, you start writing this sort of stuff at them, they're probably going to start glazing over, their eyes are going to glaze over like some of yours have done already. Okay? What you need this for is you need this to convince another statistician of what you've done. You need to be able to specify the model at some stage so that some of your peers can review it. If you're going to be the statistical consultant on these things, you need to have some model specification. The notation you find is far from standard, but you'll soon quite work out what's the minimum you need in any given journal or in a given situation to specify these things. So, finally, Fisher's approach to doing multi-comparisons. Fisher's cop-out, if you like. So, Fisher's approach to the issue of multiple comparisons. Firstly, Fisher would use an initial test at the right level of significance. Now, in this example, it's pretty easy. For one way ANOVA, that's the overall F test. And that's really testing, basically, are all the deviations the same as the control deviation, i.e. nothing? In other words, does everything not deviate from the control group? We know that tau 0 is naught by definition. If tau 1 and tau 2 and tau 3 are also 0, then really there's no differences between the groups. So, which is equivalent to no differences or no deviations between groups. Which is equivalent to saying that mu1 or mu for control equals the mu for K2O plus N equals the mean for K2O plus phosphate equaling the mean for nitrogen plus phosphate. And what's the alternative?
At least all means are different.
Yes, at least two means different, or not all means are the same. Either, both of them are logically equivalent. Okay? So, not all mu's equal. At least two of them differ. We don't know which two, but what the test tells us is there's something going on here. There is some useful results in this experiment. So if we find we've got a low p-value here, we reject the null hypothesis in favour of the alternative hypothesis, there is something going on. i.e., if we reject HA, H0 in favour of HA, i.e. our p-value is less than alpha equals 0.05, then there are significant differences between the group means. So we shouldn't be too surprised if we then go trawling a bit further and we find a significant difference between group means, because this test tells us we could expect to find that. In other words, Fisher's just sort of saying what he's using it here is as a way to sort of get in, avoid that issue of multiple comparisons, give him an excuse to make a few comparisons, a few post hoc ones, and sort of say, well, the chances are what I found was not just an artifact. Okay, then we compute Fisher's LSD. Now, don't get too excited here. It was invented a long time before the drug in the 1970s. That was Timothy O'Leary, wasn't it? Who invented LSD. So it's not the drug, it stands for least significant difference. And this is really the T. So we take the degrees of freedom for the error for 0.975. So we're not correcting, not bond for any corrected, or corrected any other way for multiple comparisons. Sigma hat, that's the square root of the mean squared error. And here it's 2 on Ni where Ni is the size of each of the levels, is the size of each of the groups. So it works. This is, assuming we've got a balanced design. In other words, that Ni is going to be the same for all of them. And that really is just the standard error we just computed. Okay? It is the standard error. This bit here is the standard error we just computed. And we're going to multiply it this time by a T for 0.975 for 3 degrees of freedom. And that's, if you like, the size of the confidence interval. If the two means differ by more than that, then the confidence interval will not include both negative and positive numbers. It'll be one side or the other. If the first one's bigger than the second one, it'll be entirely positive. If the second one's bigger than the first one, it'll be entirely negative. Okay? So if 2 means differ by more than this, that's the least significant difference for the difference between two of the groups. Hence where the LSD comes from. So, for the corn data, two groups differ significantly, and I probably should start putting this in inverted commas using Fisher's LSD and all the assumptions involved in computing that. If they differ, if the group means differ by more than and that turns out to be about 13.34. So any two means that differ by more than that, we're going to declare to be different. Significantly different in the context of this experiment with this many replications and so on and so forth, under all the usual assumptions. Does that make sense? So Fisher's approach would be do one test at the right level, compute this one statistic, and then use that to make the comparisons he intends to make. Yes, quite quickly, if he compares enough of these things pairwise, he is really doing multiple comparisons. But he's already got some assurance from the initial test that when he finds some differences, that they're probably not artifacts. So here's Fisher's approach. Here's the analysis of variance table. We passed the test with flying colours. Very low p-value. Should I really say very low p-value? All I should say really is, if I was applying decision theory as it's, classical decision theory, I should just say we have a p-value less than 0.05, which is my a priori alpha. Okay? In other words, there's something going on here. there are some differences between the group means. Here's the LSD. I've already computed the standard error above and saved it, so I've got it there. What I've got to do is change the T quantile. Oh, 15.4. So that's oh, maybe have I got the right standard error? I know what's happened here. Yeah, standard error here was 7.385. Yeah. Check my T quantile. Should be about 2.08. That's right. So LSD, yes. Okay, so well, you've still got it handy. .4. Now, here's the level means. Okay, so any two that differ by more than 15 are going to be significantly different. Well, they differ by 23, so that difference is definitely significant. These two differ by more than 15. What about these two? 12. So not significant there. And in fact, really what I was after was the one with the highest yield, but I could just take that one's 23 below the highest yield, that one's 29 below, that's minus 12 below, not 15.
What are we concerned about if they're significant between the two different treatments? Why are we not only concerned with the control?
Well, because what's the research question we're trying to answer here? What do you think? When the experimenters did this experiment, what do you think they really wanted to know? Which fertilizer gives the best yield? Okay, so what we really probably want to know is which one gives us the highest yield. Okay, so we know that the second fertilizer treatment gives us significantly better than not doing any fertilizing at all. So that's part of the answer to the research question. But then, okay, is it the only one that does that? And the answer is probably not. In the context of this experiment, fertilizer 4 also seems to be, giving some results, and not significantly worse than than fertilizer 2. Okay, so, I mean, the whole idea is you want to summarise the results to the client, the answers to the questions the client wants to know the answers to, not just give them, okay, here's your analysis, go away and you interpret this summary table. Part of your job as a statistician is to do some interpretation for them. Okay, so how would I interpret that best? Well, I think the best way to do it is graphically. So here's a bar plot of the level means. Here's a little line. What is that little line? Well, I've actually put a line that's just meets the top of the highest yielding fertilizer. I'll also put in a line at the bottom of that little line. I'll give you a label for that little line. It's the least significant difference. Okay, and so I can see quite quickly that this fertilizer is significantly better than than no fertiliser, or this one that seems to actually be retarding growth. I could move that LSD around and compare the other tops of the bars as well. Okay? So in that sort of sense, I can let the client make their own comparisons. But I've made a couple of key ones to start with. First of all, I think there is something going on here. There are some differences between the groups, but I can't conclusively on the basis of this experiment say that fertiliser 2 is by far away the only one that's going to give me specifically improved yields. What do I have to do? Well, I possibly have to repeat the experiment. These things research is always an iterative process. The results of this experiment feed into what I'm going to do in the next one. Maybe I just reduce my comparison to those two possibilities. The other thing I could do is think, well, okay, I did have some qualms about the underlying assumptions here. There were some outliers in my control group which I think were inflating my error variance. If I do something about treating those, maybe I'll reduce the LSD because I'll reduce the size of sigma squared. Okay? So I could probably tighten up the comparison by destroying some of my data and unbalancing my experiment. And I don't think that's necessarily a great way to go. A better way to go would be to sort of basically go back to the experiment and sort of say what happened with plots 1 and 2, because they were the two potential outliers.
Sorry, this might be a silly question, but...
No, I'm more than happy for a good silly question in this context.
Yeah. Could you please reiterate why doing the Fisher's approach means we don't have to worry about multiple comparisons?
Well, no, Fisher's is a different philosophical approach in the sense that sort of, okay, if you are going to use a p-value as being your be-all and end-all decision theory, say yes or no, then you really want the p-value to be, in that sort of sense, robust to most of the things that are going on around. And most of the time, that's impossible to do. You can't make the p-value the p-values actually don't really work that way. A p-value is, like the name suggests, it's a probability measure, but it's a probability measure of a fairly obscure aspect of probability. The probability of a test statistic more extreme than the observed test statistic. Okay? It's not necessarily meant to be used the way Neyman and Pearson do it as a decision-based mechanism. Okay. On the other hand, what Fisher would sort of say is, look, it's at least evidence towards there is something going on here. Okay, I've got a nice low p-value. I would say a nice low p-value suggesting that this is something that wouldn't happen necessarily by random chance, and therefore there is something going on. But are my results conclusive? Well, probably not, in the sense that I can't make definitive statements on the basis of what I've got here, but I can sort of say they are strongly indicative. Okay, so in other words, this experiment wasn't a waste of time, but what it leads me on to is, how do I answer these other questions? Which really of these two is the best one? Well, maybe I have to set up another experiment to answer that. Or, what else could I do? I mean, in this sort of context, I suspect what happened in practice, I suspect this probably was a Fisherian experiment, and that Fisher went on to do lots more of them. Because in that sort of sense, they were relatively cheap, and they cost the biggest cost in most of them was time, waiting for the corn to grow. Okay, so it's not necessarily one where everything. You've got to think about the research situation you're in as well. Repeating experiment is actually not as dire as it sounds in a lot of situations, and in fact, good science is often done by repeating your experiments and getting the same results. Really building up a body of evidence. Karl Popper used to sort of reckon we do science by repeatedly attempting to falsify things, attempting to prove them wrong. Okay, so in that sort of situation, you have to repeatedly experiment because you've got to keep proving things wrong until you get to the point, well, it doesn't like we're going to prove this wrong, therefore I accept it as being more likely to be the truth than not. Would be the Popperian approach to doing this sort of stuff. So I think you've got to think through what are you doing here, and I'm not trying to turn out a room full of trained monkeys who look at a p-value and sort of say that's the answer, because it's not the answer. The answer actually involves some interpretation of your results. Well, a lot depends what design we choose to use, what experimental design we use to choose, what model we choose to apply in what are the situations. Depends a lot on the context. What's the research question we're trying to answer? What's the variable of interest? I think I'm missing the point of your question.
Yeah. I mean, if it is not a balanced design, do you use the same way to analyze the test? Or it's just different?
Well, I mean, the argument here is that possibly we don't. If those results weren't mucked up, if there was nothing really wrong with observations 1 and 2, then we probably have to live with a situation where we are likely to have inflated variances even if we do repeat the experiment. So, what can we do there? Well, we probably shouldn't be removing observations 1 and 2. We probably can't get a good answer to the question, is there a difference between fertilizer 2 and fertilizer 4, without doing more experimentation. So the answer is we probably have to do another experiment where we just compare those two, and maybe we use 12 replicates for fertilizer 2 and 12 replicates for fertilizer 4, and we get smaller standard errors because we've got more sample size in each group. Okay, in that sort of sense, the fact that we've got an inconclusive result here informs the design of the next round of experiments. Is the way I'd look at it. Does that answer your question? Or am I just forcing you into silence by intimidation?
To just kind of understand if we can use this method only in case of the balanced design.
Well, I mean, no, you can use it in unbalanced design, but typically there's this little quirks and bubbles you have to worry about in the calculations. That's all. So so if we did remove 2 observations from the control group and we had an unbalanced design, we wouldn't necessarily be able to calculate a Fisher's LSD because we don't have the same NI in all the groups. What we'd have to do is use some sort of approximation to that, which will say the average group size as the bottom of the Fisher's LSD. So we would have to make some adjustment to that to actually make the comparison. And every time we make an adjustment, we're probably making some sort of assumption in the process. Okay. The average amount of information available in these groups is actually the average of 3 times 6 plus 1 times 4, because we've only got the group sizes we've now got. And in some ways we've got more information than that in some groups and less information than that in the others. Or we could calculate an Fisher's LSD that took still assume the same constant variance, but used N1 on the bottom and N2 on the bottom, and recalculate the standard error that way. I mean, Fisher's LSD is just basically a t-statistic times the standard error. So if it's not a balanced design, we have to recalculate that standard error.
If we had, is it possible to have a test statistic with the one where it shows that there isn't any significant difference, but then have a significant difference when we do our two-way?
There are situations you can construct them. Sometimes I suspect they're more a numerical artifact than they are anything else. So in that sort of sense, yes, you start getting mixed messages from your analysis of variance table and your summary table, and you start going, oh dear, what's happening here? It's a hint of something going wrong. Now remember, if you remember back to regression modelling, often that was a hint that we had extreme multicollinearity happening in the background. We'd get things like highly significant analysis of variance tables and no significance at all in the summary table, or vice versa. It's an indication that this is not a well-founded model for other reasons. Possibly because of multicollinearity, possibly because of some other violation of the underlying assumptions. So yes, inconsistent messages from your various bits of summary output. I like to use different bits of summary output for different purposes. I like to use the analysis of variance table to assess what should be in the model, because in the analysis of variance table, each line in the analysis of variance table corresponds to a term in the summary model. And then I look at the individual coefficients to actually answer the actual detail of the highly detailed research question. But I typically don't get to the summary table until I've got through the analysis of variance table. I use that as a filter test, like I suggest that Fisher would have done. I'm actually being very brave here saying what Fisher would have done, because I'm sure Fisher would have disagreed with me if he was here. because he was famous for being disagreeable.
Just not a deal but like where you basically observe unbalanced design. So like if we are designing an experiment, it would be stupid to make an unbalanced design.
Well, I mean, if you're designing an experiment, you've got enough resources, you keep it balanced, because basically you want to have. I mean, most situations you want to have an equal comparison of all the various different possible treatments. Okay, so I mean that sort of sense, balanced designs. The fact they're mathematically simpler is not necessarily a reason for having them. The fact that they do the job, i.e., make the comparison you want to make, is probably a better argument for them. And this is actually a question that's a bit outside the scope of this course. See me for Stat 3012 next semester. Okay. Okay. Look, I think we have to move on. So thank you for all those questions. They were good, even the one I didn't understand. And so the only other things in here was the if you were trying to actually answer different research questions, you would actually set the whole thing up slightly differently, and you would have different contrasts and different comparisons. And the brick's actually got a couple of those ones. It just plucks them out of thin air. It has a nitrogen versus non-nitrogen fertilizer comparison, and it has a bit the equivalent of a sum comparison where it compares, a fertilizer treatment with the overall mean, like a sum comparison. But I'll leave those two as exercises. The old S+ code still works, and if it doesn't, there's a new R version at the bottom of this file. I'm going to close this file now, and that's it for that one. We're going to move on to a different example. Okay, so we'll quit that and go to the workshop. Who's had a look at today's workshop? I asked quite a few questions here. Has anyone actually got some answers for me? So, it's used car trading data. So we've basically taken 18 men and 18 women, 6 members of both genders in each of 3 age categories. We gave them a similar mid-size. In fact, if you read the description in the textbook, we gave them exactly the same car. And they took this car around to 36 different used car dealers to see what they could get in the way of a trade-in for it. And I'm not sure whether these data was from a real study or from a made-up one. What do you think? Could you conduct such an experiment? Let's say you were doing marketing in our college. Would it be a sensible thing to do?
It does not make sense if the data are not gathered in the short term. It could be a successful experiment if it's a long-term experiment.
Well, I mean, okay. I suspect that all you're going to get from this is it's limited in scope, which I think is what you're getting at there. I agree with that, in the sense that all you're likely to do is get a reasonable price for the one car you've got. But I mean that's in fact an element of control in this experiment. They've used all 36 dealers have been asked to assess the same car. So that's an example of control and experimental design. It's a situation in which what you can control, you do. So there's no differences between the car because it's the same car. So the only difference is the random variation between dealers and what they're likely to offer somebody. And what we think is there's actually a systematic difference in what they're likely to offer people of different ages and different sexes. So the research question here is there sex discrimination in what dealers are likely to offer for this used car? Okay. Is it an ethical experiment? If I'm the first person who does this, I'm the first volunteer, can I actually sell the car to this used dealer? I'm purporting I'm going to, though, aren't I? Because I'm asking the dealer for a trade-in value. There's an element of deception in here. I think you'd probably have trouble getting this one through the ethics committee. because you're actually setting out to deliberately deceive 36 different people. Okay? So I think there is an element of, I'm not sure this was actually real data, I suspect it might have been made up. Okay? Now there are situations in which deception is possibly okay in some of these things, where there's no real harm done sort of caveat. But I'd be interested to see. Michael Martin actually sits on the ANU ethics committee. I'd like to see what the ethics committee had to say about that one. And the trouble is, I happen to know this particular textbook a bit too well, done by some very good statisticians, but they don't seem to be hampered by, a real push to use real data in all situations. A couple of the ones that they're obviously made up. Okay, so there, the description given in the text is a little bit different. Notice the other elements of experimental design here. We're trying to keep most things the same, but vary just sex and an age group, the two experimental factors here, the thing we think there might be discrimination on. And basically, where we can't, we try to avoid unintentional bias by, picking which volunteer goes to which car dealer at random, assigning experimental treatments to experimental units at random. Okay, so we don't just send the little old ladies to the less threatening looking car dealers. Okay, so we've got randomization, replication and control going on in the background somewhere. How many replicates have we got? How many experimental treatments are there? Basically, the 6 are the experimental treatments here are the combinations of the levels of the factor variables. So we've got 2 factor variables. We've got an age factor, which comes at 3 levels, young, middle and old. Or elderly, I think it's called here. Trying to save my feelings. And we've got sex or gender, which is at 2 levels, male and female. Okay? And therefore we've got a 2x3 two-way analysis of variance design. 2 factors, one with 3 levels, one with 2 levels, 6 experimental treatments. And we've got 6 observations for each treatment, or 6 replications for each treatment. So essentially we've repeated the entire experiment, which involves the 6 different treatments, we've repeated it 6 times. Replication within this one experiment is 6-fold. So that was I'm hoping you lot can start answering those questions about what are the experimental treatments and how many replications are there of each treatment. Because remember, I always ask a question like that on the exam. So you need to at least to pick those basic elements out of an experimental design. Okay, now this is the bit I want to go through fairly carefully because it's important and I want to make sure that we get the notation right and then we can move on to other things. So, actually I might come back to that. Let's have a look at the experiment first. This is supposed to be a workshop, not the other way around. So close that down. Open up a brand new workspace. A bit of housekeeping. So, as usual, I've given you the trade-in as a text file. I can read it in. There are my 36 observations against my... So really I've got an obvious response variable value, I've got a gender factor, and I've got an age factor. Come in with neat little labels and everything. Trust me, data almost never comes to you like that. You've taken a fair bit of cleaning to get to that point. So the names I've got to deal with are value, gender, and trade-in. And if I attach those, I can just deal with them as those names. Here's my cell means. Because let's face it, just like in a one-way analysis of variance design, what these analysis of variance models are going to model are these means somehow. So let's have a look. A sensible exploratory data analysis plot here is to plot the means. Okay, so there's a version of this in the brick for which the code has been long lost. And so I've recreated some code here that does pretty much the same job. So, young, middle, elderly, female and male. Are there any differences between the genders? Doesn't look like much of a difference between the genders, does it? They're both the red dotted line and the solid black line have pretty much the same pattern. There might be a little bit of difference going on here in how the elderly females seem to be getting a little bit worse deal than elderly males. Okay. Now that's not the only way we could have plotted that one. We could have plotted it the other way around as well. And this is by the age by gender one. So this time we've got female and male, we've got middle-aged, elderly and young. Is there a difference between the different age groups? The middle-aged seem to be getting offered more for their cars. There's some advantage to being middle-aged. Whereas the young and the elderly both seem to be getting a poor trade-in deal. Now, there's a whole bunch of stuff in the brick which fits all this stuff manually. In fact, it even does matrix multiplications and this sort of stuff. And I'll just run that code and give you a quick look at the... So it's basically having a look at they're basically estimates for each of the different age groups, because having a look at the map plot, it's pretty obvious the differences in the ages. And this is saying there's the young, there's actually it's probably elderly, middle, and young. And so the young is the bottom one, middle's that one, and there's a confidence interval for the elderly. And we seem to be getting, if you like, non-overlapping confidence intervals for the middle compared to the other two groups. Don't like that analysis at all, because it doesn't really sort of leave me by the nose for what's going on. So in fact I've redone all that. In fact you can do most of that in a single line with the current version of S+. So I've used AOV because it's an experimental design. I could have just used LM. The only difference really is it gives different output when I ask for summary. Okay. I've regressed value on age and gender, and I've told it to use some contrasts for age, and some contrasts for gender. Okay, I didn't have to set up these things. I think, in fact, the earlier stuff set up treatment contrasts. Now, there are actually 6 plots you can get. By default, you only get 1, 2, 3, and 5. Here are the 6. So there's the residual plot, and of course, in this situation, it looks like 1, 2, 3, 4, 5, 6 columns, which are the 6 groups. So fairly obviously, these are the 2 middle-aged groups, and these are the various elderly and young ones. We can't sort out which without looking at their fitted values somewhere along the line. Here's a normal quantile plot, not ringing any huge alarm bells. On that particular point, there wasn't really much of an indication of, well, this group seems to be particularly non-variable. There's more variance in some of these groups, but we could check the group variances and various other things. But let's just steam ahead for the moment. Scale location plot I don't usually talk about. Here's the plot you don't normally see, but it's quite a useful one. If you just want to start an outlier search, this is probably a pretty good one to do. This is a bar plot of Cook's distances. And typically, I look for the most extreme Cook's distance and see if it's really extreme compared to the next one down, or if it's really extreme compared to the next one down. And the answer is, no, not really. Not ringing my alarm bell, but not ringing Dennis Cook's alarm bells in terms of having a relatively high Cook's distance. And notice the size of this is 0.2 rather than 0.5. So you can almost guess what the next plot's going to look like. Well, actually, because it's an AOV, it's turned out to be this particular plot, which shows you the 6 groups sorted out, which is probably quite a nice plot in some ways, and it's standardized residuals. And notice there's 1, 2, 3 outside, 3 out of 36. That's 1/12 of my data outside, plus or minus 2 standard deviations. A bit higher than a 20th, but not that much higher. And this is the last plot, and this is what I was telling you about the other day. John Maindon and I have gone through this because he was one of the 2 people that helped write the current series of plots, and he couldn't tell me he couldn't make me understand what it was supposed to tell you, so I've got no idea what to tell you lot either. So I don't think we'll look at plot 6 again. In fact, what I'll probably do from now on is I'll just change the defaults so that we get plots 1, 2, 4 and 5, because I'm not particularly interested in plot 3 either. I don't think it shows you anything that you can't see on plot 1. Okay, so we could just change the defaults from now on, but I don't think I've done it in the rest of this one. So here's the summary, and of course, because it's an AOV model, this becomes the analysis of variance summary. And what does that tell me?
The effect of gender on responsible variable is not so significant.
Well, yes. Well, age does matter. I think is the more, I'd put them the other way around. Age does matter, gender doesn't. It seems to be in this context. And then you could go and have a look at these, but I would have thought it's a bit premature at this stage. However, I would argue this is probably the model that most of them would have had in mind when they designed this experiment. Remember, when you design the experiment, you decide you know what's included a priori, you really have a model in mind when you design the experiment. And I suspect for most of these things, when you've got strong design features like these, you probably are at least intending to check if there's something different going on for particular ages and genders. So you remember back on our plots, is there something different about a particular age and gender combination? Well, is it really, should this F be like this, the same sort of pattern here, or are really little old ladies really getting stiffed? Is it because they're not only old, but they're also female, that they're getting a worse deal? And in that sense, what I'm looking for is is there a combination of the different factors that makes a difference? And because I'm interested in those combinations, I probably would have a priori have had a model with interaction included. Even though interactions are hard to interpret, I would probably sort of try and rule them out. In other words, I would think that this is probably my design model for this situation, where I have a main effect for age, a main effect for gender, an interaction between age and gender. All set up with some contrasts. Notice I could have used age star gender instead of age plus gender plus age gender. I just wrote it out in full. That's a very handy sort of shorthand for later on. Okay? Let's have a look at that. Does it give me better residual plots? Or no, at least no worse residual plots? Oh, good. Well, they're certainly no worse. Mm, 24 is stretching things a bit now. But again, in fact, if anything, I've only got one of my 36 outside of my plus or minus 2. In fact, if anything, I think it's a slightly better fitting model. I still don't think there's any excuse, despite the fact that 24 is so prominently labelled on these plots, to go around deleting it when I'm balancing my experiment in the process. That's the young female group. Maybe 24 was particularly attractive young lady. And we are dealing with middle-aged men, used car dealers here. Okay. And again, no idea. One of these days I will sit down and work out exactly what they're trying to do here. But I don't, the point hasn't been made well for me. You can read the help files if you want to get a bit more information on that. Okay, so here's the summary. What's going on? Well, there's a strong age effect. There doesn't seem to be any gender effect, and there doesn't seem to be anything going for particular combinations of age and gender. So there might be an apparent difference in the matrix plots between the elderly males and the elderly females, but it's not enough to sort of to get the magical ball balancing seal significance. Okay, that seems to be the message you're getting from here. In other words, when we do the interpretation, we would concentrate on the differences between age to do the interpretation, which is what that early analysis did. It calculated confidence intervals for each of the age groups. Would I refine this model? Here's one of the big differences between an experimental design model and an observational model. If this was a designed experiment and that was the model I had in mind when I designed the experiment, I would leave everything in. The fact that now I can sort of say there doesn't seem to be a gender effect and there doesn't seem to be an age-gender interaction is in fact, if you like, a negative result. I included these things in my whole experimental design, in my design model, in the belief that there might have been a difference here. But really, it's what I've got here is a result that sort of says that's not the case. So remembering research is always an iterative process, it means I possibly don't have to worry about an age difference in the next iteration. Gender difference in the next iteration. I just have to worry about concentrating on the age difference. But in that sort of sense, the whole issue of a reference model differs from the observational models to an experimental design one. With an observational model, typically your reference model was a null model, and you included things in if they were significant, and you threw them out if they weren't. Not always going to be the way you deal with these models. If you have something that's an a priori part of your design, if it's part of your research question, that puts it in the model. If it's part of the research question, in the sense that says, I believe that this is going to make a significant effect, you put that term in the model, it turns out to be not significant, you have a result. What your assumption of that it was going to be important is wrong. Okay? It's a what goes into the reference model is not necessarily just a null model. There's a strong thing in an experimental design that you designed these things before you started and you should stick to them. In other words, the right error mean square here for all the comparisons should be this one, which is slightly smaller than the error mean square you get if you deleted that and that. Okay? In other words, you get a tighter comparison by including these slightly insignificant non-events in there. That's another reason for doing it. Not the good reason, though. The good reason is because you designed it. It was part of the design when you designed the experiment. So that was the answer to the question about in the workshop here. That last bit, think through those issues. Don't always just throw things out and refine them out of there because they're not important, because they don't seem to be significant. That's not necessarily the criteria. You're trying to think about how do I weigh up the evidence to answer the research question I had when I started.
Why wouldn't you do both? Like, first do the experiment and then use it observationally as like your next experiment?
The bottom line is we end up doing a bit of both in practice. Okay, so I mean, typically, yes, you would probably feed this information. I would probably keep, if I had these strong assumptions, and I articulated before we actually did the experiment, that would be my reference model, and I'd stick with it. And I'd take the fact that age colon, the gender and gender, age colon gender were not significant. I'd take those as being results of the experiment, negative results in the sense that these don't make a difference. But I'd probably feed that information to the next iteration of the experiment and design a different experiment next time that didn't necessarily bother about those factors because they didn't seem to be significant in this one. And I really wanted to sort of tie down what the age discrimination was. Okay. Notice I'm going to expand things a bit here. I'm going to get you some cell means. Oh, so I haven't done some age means, some gender means, and an overall mean. And let's compare those with the coefficients from one of the models. Let's compare it the coefficient with this one first of all. First of all, because I've used some contrast, what do you notice? That's the overall mean that was offered to all 36. Okay, and so we're seeing deviations away from that overall mean. Like that's the average price I'm going to get for this car. If I go to the gender one, 23 this minus this gets me to 23.1667, the female mean. This minus the minus of this, i.e. plus 0.389, gets me to the male. Okay, so you see how the sum contrasts work? Those two, the two coefficients for gender, the one for females, which is the first one, which I've got, and the one I haven't got, which is the negative of it, because the two of them have to add up to 0, they basically get me back to the means for those particular groups. If I go up a bit, okay, the elderly. Well, 23.5 minus 2 point that gives me that. 23 plus that gives me that. If I add those two together and take the negative of it and add that to that, it'll be minus 2 something, gets me to 21.5. Okay, because the gender age 1 plus age 2 plus the missing age 3 sum to 0, and so I get the age 3 We want to get to young by taking that plus that and taking the negative of it, which is negative 2 and a bit. Off that gives me 21.5. Make sense? In other words, from this fully saturated model, I can recover all of those. In fact, I can recover all of those from the model without interaction with a balanced design. Because, in fact, all these things up here would have been exactly the same. Where do these get me? Well, they're the extra bit. I've got to go, having got from, if I want to get to the elderly female group, I have to go 23.556. It's the first age group, so I have to take minus 2.31889. It's the first gender, so I have to take off another 0.3889. I have to take off this one here. And then I have to take off age 1, gender 1, that bit as well. And that will get me to the exact cell mean for the elderly females. Okay, so really these models are just modelling the group means with random variation around them. Okay, what's in that random variation? Well, truly random variation between the real estate, between the used car dealers. Okay, but also because they vary naturally from person to person. But there's also anything I haven't controlled for, anything I haven't counted for in the model, also gets subsumed into that error. So if I take out the interaction term, that goes back into the error. Okay? Even though it wasn't significant, it will still increase the error if I put it there. So the error is a combination of stuff that I possibly did know about and could have accounted for, and true random, underlying random variation, natural variation. So I'll start this now, but I'm going to have to finish it next week, I suspect. We'll have a quick look at the writing that model out, because it's good practice to do this occasionally. It's also tedious. So, here's the model. I'm going to need 3 subscripts. Why? Because I've got 2 factors, and the first 2 factors are going to describe, the first 2 subscripts are going to describe the levels of those factors, and the third subscript is going to describe the number of replications in each one. Now, instead of using beta naught, I'm going to use mu. Why? Because I use some contrasts, and in fact the intercept here is the overall mean. So, good symbol for it, let's use it. Here's my age factor. Here's my gender factor. Here's my age-gender interaction. Notice that I use it has 2 subscripts because it involves both age and gender. If you like, the I's are modelling age, the levels of age, and the J's are modelling the levels of gender. And where the assumptions, of course, being the usual assumptions that the EIJKs are IID normal 0 sigma squared. Then I have to specify the levels of I. These will be alphabetical order because I've let, I didn't set up the contrast myself explicitly. I let I use its defaults, and it defaults to doing things alphabetically. And with some contrasts, it uses the last one as its reference group, and it fits parameters for the first two in alphabetical order. They're the levels of age. J is 1 female, 2 male, because female comes before male alphabetically. That's the levels of gender. So the R default is alphabetical. So actually alphanumeric. I think it counts numbers before it counts letters. And K equals 1, 2, 3, 4, 5, 6 observations for all ij. And if you like, N is basically 3 levels of age times 2 levels of gender times 6 observations equals 36. So I've got 6 treatments, 6 applications of each to give me my 36 observations. Your homework, your mission should choose to accept it, is to work out how I'm going to specify the constraints for sum coding with 2 different factors. It's not particularly hard, a bit tedious, and it's going to take me too long, so we're going to finish now. Yeah, so the point I was making there was that with the default plots you can get for an LM object, there are in fact 6 of them hidden in the background. By default we get 1, 2, 3 and 5. 4 is useful, so I wouldn't mind seeing 4. I don't particularly like 3, so we might lose it, and I don't understand 6. No, it means I'd like somebody to explain it to me. I mean, I did try asking John, but I've got nowhere with that one. So. And he wrote it. I'm sorry, I'm really deaf in this sort of environment. I mean, you can either wait a little while until he's gone after he's clearing up, and then I can answer a question where I can actually agree and this sort of stuff. Or you can come and see me tomorrow. These notes, I put them all on water. They all get onto water eventually. Same point. And I'd like to look for each number as far as this is concerned. That should be a number as far as this is concerned. I can get it out. I can wait until you put it up. Yeah, that would be good. But by that stage, of course, most of the herd has disappeared as well, and I'm fighting a chance of hearing it. So. Yeah, hopefully. So I got it in. Now, of course, it's pouring rain for us to get ready to see the
他所有的你都要说出一个收获，其实你说出来收获才是最重要的，你没有收获其实就没有意思。